Hello everyone, I'm Paul and today we're solving problem 3577. Count the number of computer unlocking permutations. This is medium and the key to solve this is observation. So let's start. As you can see, this is a reading problem, so I highly recommend you to read this and try to come up with the solution. Reading is also part of the problem. We are given an array complexity, so let's say that this is the array, and every element here corresponds to the complexity of a unique password to unlock a computer. So for example, this is the complexity of the password to unlock computer number 0. Now here it says that computer number 0 is already unlocked. And here it says that we can use previously unlocked computers to unlock new computers only if the index of the unlocked computer is smaller than the current index and the complexity of the unlocked computer is smaller than the complexity of the locked computer. So let's say that we are trying to unlock computer number 1. Well, we have a computer that's already unlocked and the index of that computer is smaller than the current index, and we also know that the complexity of that computer is smaller than the current complexity. We meet these two requirements, so we can unlock this computer 2. And now we can unlock computer number 2 with either computer 0 or computer 1. Remember that these two passwords are already unlocked and we can use them here. So this is now unlocked also. Our job is here. We need to return the number of permutations that represent a valid order in which computers can be unlocked. So this is one valid permutation, and if we take an array with 1, 3, 2, this is another valid permutation. Remember that this is already unlocked, so we can use it to unlock this computer, and then we can use this again to unlock this computer. We can unlock every computer with this permutation. And given that we have 2 valid permutations only, we return 2. And this is very important. Only the element corresponding to index 0 of the initial array is unlocked. This means that if we take an array with 3, 1, 2, for example, this 3 is not unlocked. Only the 1 is unlocked, only this. So in this case, we will never be able to unlock this computer. That's why this is not a valid permutation. So this means that we need to filter every permutation where this computer is not at index 0, because we know that all of those permutations will be invalid. So we can fix this position and count only the permutations for the next elements. If we fix index 0, in this case, this is one valid permutation and this is the other valid permutation. We only have 2 valid permutations if we fix this first element, so that's why we return 2. Now, in case you don't know this, we can get the total number of permutations of some array by doing n factorial, the total number of elements factorial. Now here we are fixing index 0, so we are actually doing n minus 1 factorial. We only care about the permutations of every element except for index 0. And here n is 3, n minus 1 is 2, 2 factorial is 2, so that's why the result in this case is 2. Now what if we have something like this? We know that computer number 0 is already unlocked, and we can use this to unlock computer number 1. Now what about computer number 2? We will never be able to unlock this because 1 is smaller than 2 and it's smaller than 3. Now what if we try a different permutation? Remember that we are fixing index 0, so the only permutation that we can take here is 2, 1, 3. Well, in this case, this is already unlocked, and now we can't unlock this one. Why? Well, because 1 is smaller than 2. So we don't even need to compare this and these numbers. We can compare this with index 0 right away, and if this is smaller than the element at index 0, Well, we know that we will never be able to find a valid permutation. So in this case, we just return 0. So we can just iterate this from left to right from index 1. First, we are here and we are checking if the current number is smaller or equal to the element at index 0. Here 3 is greater than 2, so we continue. And now we are here. And we are checking if 1 is smaller or equal to this element. And it is. So at this point we can just break the loop and return 0. Now if here we have a 4, instead we can return n minus 1 factorial, meaning 3 minus 1 factorial, which is 2. So with this in mind, now let's go with the code. N is initially the length of complexity, and now we can just iterate every index from 1 to n and check if the current complexity is smaller or equal to complexity for index 0. And if it is, we just return 0. Else, if we reach the end of this loop and we never return 0, we return factorial of n minus 1 modulo the required value, which is 10 to the power of 9 plus 7. This is in the problem description. So this is the entire code. Now let's submit this. As you can see, this works and it's efficient. Time complexity here is big O of n and space complexity is big O of 1. As you can see, we have room for improvement, and that's because of the following. This factorial is very expensive, so what we can do instead is we can pre-process every possible factorial. We have a mod value which is 10 to the power of 9 plus 7, and the maximum value for n, the maximum number of elements that we can have, is 10 to the power of 5. And this is included, so here we just add 1. We have a factorial array, which is an array with 1 times mx. And now for every index in range from 1 to mx, every time factorial I is factorial I minus 1 times I. And we have a mod value, so this is modulo mod. And now down here we can just return factorial of n minus 1. So let's submit this. And as you can see, this is way more efficient. So if you found this useful, please drop a like, subscribe, and see you in the next one. Bye bye.